Okay, today we're gonna try to solve 226 invert binary tree. So we're given the root of a binary tree and we basically just want to invert it and return its root. Okay, so for the first example, we have an input of 42713969 and we're really just returning all the nodes and its children in a inverted manner. Okay, well, the first thing I would probably do, or a brute force approach, is I'll just check the left and the right sides and I would just swap them. However, in this first example, okay, we're given it's a binary tree, so that's good. Let's see the constraints. The number of nodes in the trees is in the range 0 to 100. Okay. Now, would I use breadth first search or depth first search? I'm pretty sure Python has like a recursive limiting restraint or something. So, I might lean away from using depth first search for this, or at least the recursive approach. So, first of all, let's just draw this out. So, we have 4, 2, 7, 1, 3, 6, and 9. So I'm just gonna annotate it a bit. Okay, we want to invert this. The first thing we have to do is we have to look at its two parent child. So that would be node left and node right. So the root node stays the same, right? So we can definitely just return the value, the node.val. So we're definitely going to be returning like node.val, because we want the value and not just the count of the nodes. And following that, we want to swap the two nodes. However, I do wonder, can there be cases where there's only one left side or only just one right side, like where the counterpart side is missing? That is something to consider. So 7-2 swapped, then we check the third level. So we first checked the first level, now we're checking the second level, and then the third level is gonna have 4 nodes. So 6, 9, 1, 3, and we basically, okay, we might have to check brute force wise. We'll check the left child's child, so that would be 1, and we want to swap that. We want to swap 1 with 9, so the right child's right child. Okay, that would be my brute force approach. So that would make 9 and 1 swap, and that would make 6 and 3 swap. Okay, so that we invert it. Okay, I'm thinking, what about if we just traverse through the entire graph? Okay, generically, what if we just traverse through the entire graph, and then kind of, let me see. We traverse through the entire graph using a breadth first search, and then swapping. Okay, but if we swap it, it wouldn't swap 1 and 9. Rather, it would swap the two children of the child node to the root node. Okay, wait, hold up. We can just swap the children. Wait, can we just swap the children instead? Okay, we could perform a swap on the children of 2, then swap it with 7. Okay, that's another alternative. Okay, what about edge cases? We have this 213 becomes 231. Okay. Okay, I'm gonna make a I'm going to import deck just to start things off. Import, okay, we're going to do from collections, import deck. I used to call it deque. I don't know if it's the right way, but I think it's called deck. And okay, we've got our deck. We can create our que equals to our deck and our root node. So let's make our que. So we've got our root node within our que. In this example 2 case, it would be 2. And alright then, let's traverse through the first layer. So we can say while que, and the question becomes, do we care about each level's size? I don't think so, not necessarily, because we really just want to fine, okay, so for the first value we can say, we can pop the first value because we are performing a breadth first search, so do pop left. So this will pop the root node, and we're going to append it to our que. So we can, actually we don't want to append that to our que. We'll make a new value. We'll call it, we'll make it a list. We'll say inverted tree. Okay, just initialize it. Empty for now. Again, before that, I might actually just do inverted tree dot append our root node. I don't know if we can do that. And if so for the left node, we're just gonna append to our que dot append node dot left, and same for the right. So we'll do if node dot right, then we will do que dot append our right node node dot right. Right? Just run it to make sure there's no syntax errors or anything like that. Okay, I guess that makes sense. And let's just return. Okay, we'll just return something then. Return. Okay, just for now, we'll return the inverted tree. Okay, that should theoretically return our root. So for type tree node value none. Okay. Okay. Okay, you know what, we'll just handle the edge case first. So we'll do if not root, we will return none. Just like that. Run that. Actually, we should return an empty list. Empty list. That makes more sense. Type error tree node, right tree node val left, right none. Okay. I mean, that makes sense. If I just remove that. Hint please. Okay. Something. Okay, yeah, I'm fumbling hard. Okay. Where's my shoes? Alright. You know, we'll just perform a swap. I don't know if this will work, but we're just gonna perform a swap. So we'll do node.left, node.right. We're gonna swap it simultaneously. I don't want to use a temp variable. And we'll make node.left is equal to the node.right, and we'll make the node.right is equal to the node.left. I hope this fixes the error. What did I do? Oh, I forgot. Okay, we'll just return the root for now. Okay, it might actually be this. Oh, you can't return this for a tree node? Alright, fine. What happens if we return none? Okay. Well, I learned something new. Apparently you can return none, and they'll give you this format. Submit it. Wait, what? Oh, wow. Okay, I didn't expect that. Alright. That's it.